Good morning. Welcome to Wednesday. Today we're going to talk about a new topic: uniform circular motion. All right, so that's what's on the agenda today. And before we get started, I want to remind you that there's a homework assignment due Friday. I think that's still doable. And Friday, we're going to have our weekly recitation session, so please sign up if you can come. I really enjoy seeing you in person, at least seeing your eyes, part of your face in person. So Friday, don't forget to sign up so that there's a space for you, since we have limited capacity. Last week there's more space than people signed up, so that's good. It means that there's nobody being left behind. But make sure you do sign up before you come on Friday. It's a good time to ask me questions about homework that you're stuck on, concept questions. And today we're going to take a look at some clicker questions. These are concept questions if we have time, and if we don't, we'll do that on Friday too. All right. So if you got any questions, put them in the comments as I'm talking. And I posted a projectile motion tutorial a few days ago, and it looks like, well, Holly's taken a look at it and said it was very helpful, so that's great. So please, use these resources. There's something about remote teaching, which, remote teaching makes it harder for us to stay connected, and for me to get a sense that you know what you need to be doing in order to succeed. There's, I guess, less feedback coming from you guys. So just make sure that you're using the resources that I post for you. All right. Hi, William. Hi, Steve. Hi, Mike. All right. So uniform circular motion. So let me draw a picture and ask you some questions about this picture and see if we can uncover some new physics. All right. Okay. So here's the situation. You have, let's have a title, uniform circular motion. Okay, so here's the scenario. There's an object, and maybe it's a planet orbiting the sun or a satellite orbiting the Earth, but it has a path that's circular. Okay, so it's going around in a path, and at any moment in time, oop, that didn't work out right. Why? This thing has a velocity. So the velocity vector, the vector for this thing's velocity, is tangent to its path. So as this thing moves around, it's moving this way. When it gets over here, now its velocity vector is going to look something like that. When it gets over here, its velocity vector is going to be like that, and so forth. Okay, so its velocity vector is always tangent to its circular path. So my question is this scenario constant velocity? I should have said that. Well, let's see what you say. Is this scenario constant velocity? What do you say? I should have said that the uniform part means that at any given moment, if you want to quantify its how fast it's going, you get a number that would be the same quantity, the same magnitude, meters per second, whatever, 10 meters per second, 5 meters per second. So you can assume the uniform part of this includes that the speed is constant. Okay, so I have a situation where the speed is constant, but the velocity, does that mean the velocity is constant as well? So Chris has got an answer here. He says no, because there's change in direction. All right, good. So velocity is a vector quantity. It has two parts. Vectors have two parts, a magnitude and a direction. So if either of those things are changing, then the velocity is not constant. Okay, another way of saying that is, in this case we have these two things, direction and speed. The speed is constant, but the direction is not. So velocity is not constant because direction is changing. All right. So let me show you a page in your textbook. Just gotta change the source here. There we go. All right. I hear my kids screaming upstairs. Gosh, I can't wait until they go back to school. Okay, so the chapter, chapter 4, section 4 is called Uniform Circular Motion, and there's let me zoom out here so you can see more of this. So it starts with we'll call this a geometric proof of this quantity, which is called centripetal acceleration. Okay, so I'm getting ahead of myself. If the velocity is changing, then that means that there's an acceleration. There's an acceleration. That's the definition of acceleration. Acceleration is a change in velocity. And we know that the acceleration isn't causing the speed to change. The acceleration is causing the direction to change. And then it remains to uncover the nature of this acceleration. It has a magnitude. It's a vector quantity too, so it has a magnitude and a direction. And so in the textbook, we're not going to go through this again, but it's worth taking a look at. Spend 5 minutes looking at this. Call it a geometric proof of the fact that you can show that if you have a situation like this, where an object is doing circular motion and it's uniform, and part of that is there's a constant speed, the other part of it is that the radius of its path is constant. So uniform has two parts, constant radius, constant speed. And so this geometric proof is showing that if you have this condition, the acceleration that's causing the change of direction is center pointing. Center pointing means centripetal. Center pointing is the word centripetal means center pointing. So we call this a centripetal acceleration. So the things that are uniform about this are V is constant, speed, and R is constant. And if those two conditions are met, what you can show is that there's a center pointing acceleration at any moment of time. And this is called centripetal acceleration. All right, centripetal means center pointing. And the way that this is proven in the textbook is, in this geometric proof, it sets up the situation, well, you could quantify the change in velocity as you move from one place to another, and that's related to a change in angular position, angular displacement, and then there's a linear distance, delta r, which is related to the arc length, and you can argue that in the limit where these delta v's and delta t's get really, really small, the centripetal acceleration is center pointing, and the magnitude is v squared over r. So this is pretty interesting, actually. You have something doing a circular path, and the magnitude of the acceleration that's causing that circular path is a function of the radius of the path itself. Well, it's a function of 1 over the radius of that circular path, and it's a function of v squared, the speed squared. All right, so I'm going to write this down and then ask you some conceptual questions about what this means. So the magnitude of this thing is v squared over r. Okay. So here's a question for you. Well, this is a scenario. So imagine you're in a car. Or not, you don't have to imagine it. You've all been in a car. I want this erase. Just cross it out. You're in a car. Okay, and you're going around a turn. So this is your car looking down from above, going down the road. Here's the road, and then the road turns. Okay, so your car turns too. But at any moment, its instantaneous velocity is tangent to this circular path that it's following. So my question is, what does it feel like? You know, from your perspective, you're in this car riding along. What does it feel like when you go around a turn? There's a little bit of foreshadowing here because we're going to get a connection with forces pretty soon. What does it feel like? What does this feel like? Well, while you're thinking about this, let's expand the scenario a little bit. What does it feel like to go fast around a turn versus go slow around a turn? What does it feel like to go around a tight turn versus a gradual turn? What did those different scenarios feel like? Let's see. Holly says it feels like I'm sliding to the side during this fast turn. So you feel, it feels like there's something pushing you. I think that's what Holly's saying. It feels like it's something pushing you. Could you qualify that a little more? What direction does it feel like you're being pushed when you go around a turn? Can you Can you conjure up a memory of going around a turn? What does the experience feel like? I'm getting pushed to the outside of the circle. Just this in my car for application. Sullivan Steel, are you are you driving right now? You get whipped out opposite the direction of the turn. So yes, okay. So the experience is that you feel like, going down the road and there's a turn and I'm going to go this way. The experience is it feels like there's something pushing me the other way. And but I'm gonna let you in on a little secret here. All right, and this is, maybe this will blow your mind a little bit. When you're going down the road and you make a turn, turn's going this way, and you feel like you're being pushed out away from the direction you're turning, that's not really happening. There is nothing pushing you away from the direction you're turning. It's not happening. It's not real. It feels real. It feels like you're being pushed in this direction. All right? That's not real. All right, but here's the next part. You're actually being pushed in the other direction. Your body is being pushed in the direction you're turning. Is that just kind of put holes in your experience of reality a little bit? So let me say that one more time. When you go around the turn, you're in a car and you go around the turn, it feels like you're being pushed away from the direction you're turning, but that's not real. What's actually happening is there's something pushing you in the other direction. All right, so we'll fill in more pieces of this to give you more understanding in the next couple weeks. But for now, let me add to this foreshadowing a little bit. Holly, explain this now. Let me add to the foreshadowing a little bit. So you're doing circular motion when you go around a turn, and for that time when you're going around the turn, it's probably well approximated as uniform circular motion. There's the radius, the curve has a radius, and you're moving with constant speed, and the fact that you're accelerating toward the center of the circle means that there's a force pushing you in that direction. All right, so here's the foreshadowing. Forces in physics are pushes and pulls, and they cause accelerations. Okay, so forces are the cause of accelerations, and forces are directly proportional. This little fish symbol means directly proportional to the acceleration. There's a proportionality constant, which we call mass. Okay, we'll add that later. But for now, I just want you to think about this conceptually. Forces cause accelerations, and the forces the accelerations that you experience are directly proportional to the forces acting on you. And these are vector quantities. Shouldn't be surprising. Forces are pushes or pulls, and forces are pushes or pulls, and they are there's direction associated with that. That shouldn't be controversial. Pushes and pulls have direction, and they have magnitudes. So forces are vector quantities, just like accelerations. So when I say that, a force is directly proportional to the acceleration, or acceleration is directly proportional to force, and they're both vectors, that means they have to point in the same direction if they're proportional to one another directly. And so if you're accelerating toward the center of a circle, that means there's a force pushing you in that direction. Okay. So we'll add some more. Holly wants to know the answer now, but you can read ahead. And it's not so much the answer as just a description of what the world is like. Physics is, we like, humans, we like our answers to answer questions about why. Why is that? And, in physics, there's certainly cause and effect. You can, why does something accelerate? Because there's a force pushing on it. But there's other things which, we'll learn, which don't really have an answer to the why question. It's like, why is mass this thing that connects force and acceleration? And it turns out there's different ways that you can define mass. You can say, well, mass is this thing that connects forces and accelerations, but mass is also defined in terms of a fundamental force we call gravity. Mass causes gravitational attraction, and physicists call this the definition of mass, which relates forces and accelerations, is called inertial mass, and the definition of mass that involves gravitational attraction is called gravitational mass. And as far as we can tell, those two ways of defining mass give you equivalent numbers for mass, but the connection isn't really that straightforward or even obvious. So anyway, okay, I'm getting ahead of myself, but let's go back here and let me ask you another question about this experience. Maybe change this to. I guess I can't zoom out anymore. All right. Hello, computer. Stop moving. So, you have like these amusement rides, that are like these cylinders, and they spin around really fast. They spin around in a circle. And then, I remember when I was a kid, growing up, there was a ride like this in Rehoboth Beach called the Galvatron. I think that's what it's called. Sounds like a transformer. Galvatron, something like that. And once it got spinning pretty fast, you were like, your back was on this little thing that was padded, but once you got going really fast, it slid up the wall, so your feet were off the ground. But most of you, I don't know, if I did that today, I'd probably get sick and throw up. But that's because I'm old now and there's problems with my vestibular system. But most of you have experienced something like this kind of carnival ride, and so this is an example of uniform circular motion once you get up to speed. But there's a process of accelerating in speed. So this is a case where at any moment your acceleration has this centripetal component, the center pointing component, but there's also a component that's tangent to your path, and that's adding to your speed. All right, so the acceleration is a little bit different, but the experience that you have is that the faster you go, the more it feels like you're being pushed out against the wall. And so you can, what's really happening isn't that you're pushing out what's really happening is there's nothing pushing you out against the wall, even though it feels like that. What's really happening is the wall is pushing on you harder. But we can see, in this definition of centripetal acceleration right here, that the acceleration that you experience is proportional to how fast you're traveling squared. So the faster you go, the more acceleration you have, and that means the more force is necessary to experience that acceleration. All right. The other thing is that this inverse relationship to r, when people are designing highways, highway speed limits are much higher than country backroad speed limits. So country backroads can have very windy roads and turns because you're going slow, but on a highway, the road is the turns are much more gradual, and that's because if you make r bigger for a given speed, if you make r bigger, you make a smaller, the rate of acceleration smaller. So it's easier to negotiate that turn. You do it more gradually. All right. So let's set up a problem. I want to do, so just like I did the projectile motion tutorial, I'd like to do a tutorial on uniform circular motion, which involves a satellite in geostationary orbit. Okay, and to do this problem, I've got to add something that is a little bit ahead of where we are. We've got to quantify the force of gravity. So I'm going to do this tutorial. It'll be a good tutorial on uniform circular motion for this material, but it's also looking ahead to how forces come into our understanding of accelerations. All right, so look for that. It'll be in a couple days. But let's take a look at one of these homework problems and see if we can figure it out. I'll save that for you. I mean, these problems are pretty. I don't know. That's pretty easy. Let's do number 7. 7's the hardest one, I think. Mainly because there's some unit conversions here. All right. I can't get to a new. All right, a fan is rotating at a constant 351 revolutions per minute. What is the magnitude of the acceleration in meters per second squared of a point on one of its blades 11 centimeters from the axis of rotation? All right, so there's some new jargon here. The acceleration is going to be a centripetal acceleration, a center pointing acceleration, because the blades are going in a circle. The axis of rotation is the center point of its path. And revolutions per minute is, it may not look like it, but that is actually a measure of speed. We have to do a little bit of work to see the connection. All right, so I'll go out here. Okay. All right. So let me draw. So I read the problem. I want to apply my template, my technique, my framework for problem solving. So step 1, read the problem. Whoa. Okay, step 2, draw a picture. And so here, there's a fan, and the fan has blades. Oops. Wow, that's horrible. I'm trying to be too fancy. You have a fan that has blades. There we go. They're all supposed to be the same size. And the question is about, there's a point on the blade which is a certain distance r away from the center point of rotation. So this center point is right here is the axis of rotation, called the AR. So you have this point on the blade out here, a certain distance away, and the blade is rotating, so there's a velocity associated with that point. And so what I know, let's see, I know next step is write down my knowns and unknowns. Okay, so the things I know are, I'll write V equals 351 revolutions per minute. Okay, so it may not be clear that that is in fact of speed, but it is. And R is 11 centimeters. I'll write it out as 0.11 meters. Okay, that's what we know. And what we're after is A, the centripetal acceleration, the center pointing acceleration, and the derivation in the textbook tells us the magnitude of that acceleration. It's center pointing, so we know the direction. The magnitude is speed squared over r. So if I took 351 and squared it and divided by 0.11, I would not get the right answer. Okay, so let's see if you guys can figure this out. So speed, the standard units, the SI units for speed are meters per second. How can you go from revolutions per minute to meters per second? Well, let's not talk about the minutes to seconds, because you guys know there's 60 seconds in a minute, okay? So that's not hard. But my question here is, how do you go from revolutions to meters? What's the connection? First, we need the circumference to convert the revolutions. Good. So Holly's on to something here. If you think about this, one revolution has a distance associated with it, and speed is a distance divided by a time. And so if you know how long the distance is to go around the circle one time, and you know how long it takes, then you can figure out a speed in standard units of meters per second. All right, so that's the key. You got to connect circumference with revolutions. Okay. So we have so step 4 is connect the knowns with the unknowns. So we did that over here. Step 5, solve. Step 6, check. Okay, if we can. Okay, so let's think about a circle. So we have this point on a circle, on a fan that's going around in a circle. So there's a radius associated with that, and the speed of that point on this fan blade can be found if you know the distance it travels in a given unit of time. Okay, and the distance it travels is related to the circumference of the circular path, 2 pi r. And the time it takes to go around once is called period, which is often abbreviated T. So the period of its rotation is how long it takes to go around once. How far does it travel? 2 pi r. And if you take the ratio of those two things, you get speed. Okay. Let's think about if you have revolutions per minute. Let's use a different color. So if I have 351 revolutions in 1 minute, and I want to convert to meters per second, what I can do is I can say, well, I can first multiply by 1 minute is 60 seconds. And I'll get rid of the minutes and introduce seconds. So now I would have revolutions per second. But now I leverage this connection with the circumference. 2 pi r, which is the circumference, meters is 1 revolution. So the revolutions will cancel, and what I'll be left with is meters per second. Okay, so if I do that conversion, you might say, well, we don't know, well, we do know r, so we can calculate that. So 351 times 2 times pi times 0.11 meters divided by 60, I get, let's go up here, V equals 4.043 meters per second. Okay, so now I have V, I have R, I can find A. Just square that and divide by R. $148.6 meters per second squared. All right, let me put that in here and check to see if we're good. And we're good. All right. So let's do this let's do this algebraically and see if we can get us a formula for finding the answer without doing too much work ahead of time. So this approach is useful a lot of times. What I'm saying is, if we go down here, if we have V in revolutions per minute, and this is telling us if we multiply by 2 pi r over 60, that's going to lead to V in units of meters per second. So another way that we could have approached this is we could just say, well, the centripetal acceleration is RV times 2 pi r over 60 squared over r, which will simplify to V 4 pi squared r over 60. So is this, what I'm saying now is if you derive this formula here, the V is in revolutions per minute and the r is in meters. So we're just algebraically solving for centripetal acceleration using the units that were given to us. And in this case, you had an r squared in the numerator and an r in the denominator, so one of the r's canceled. And you have this relationship that's showing a direct relationship between r and an acceleration. Let me say it this way. So for this particular problem, if you write it like this, it gives you a little bit of conceptual insight, and it goes something like this. If your speed is in units of revolutions per minute, think of a fan blade. I wish I had one here to show you. Here you go. This pen, this marker is my fan blade. So it's going around in a circle. And it's it's a solid object. So it's made up of an infinite number of points along its length. There's a point here in the middle, a point at the end, a point here closer to the axis of rotation. But what's true about all those points is they are all making the same number of revolutions per minute. So when you have a speed that's given in units of revolutions per minute, or alternatively, we'll see later this semester, we'll see units like radians per second or degrees per second. It's angular units. What you really have is something called an angular speed. Okay, but for the purposes of this, thinking about this, we have a situation where every point on the fan blade has the same angular speed in revolutions per minute. And what this formula is telling us is that if you put in, that when we write things like this is really an angular speed, which we write as omega. And what this is telling us is that the centripetal acceleration in cases like this is a function of r. So objects that are further out have a greater centripetal acceleration than objects that are close in. So if you connect with the forces that are causing these accelerations, I know that it would feel like the point on the fan blade is being pushed out, but what I told you earlier is it's actually being pushed in. It's moving in a circle. So let me give you an experience you've had that connects with this physics. All right, so here it is. You're at Morgan Grove Park, and there's a merry-go-round there. One of these things. It's like a disc. It's got a railing, and it's on like a little pivot thing, and it spins around really, really fast. And kids like to sit on that, and adults throw up when they get on them. All right, you know what I'm talking about? So these merry-go-rounds, most of you have been on one at some point in your life. Think about what it feels like if you're riding on one of these things, if you're near the center, near the axis of rotation, versus further out. And see if you can conjure up a memory of what that feels like. Maybe you can do a field trip over the Morgan Grove and experience this. And the experience you'll have is it's much harder to hold on and stay on and not get thrown off if you're near the outside, near the outer edge. And it's much easier. In fact, if you're right in the middle, you can just kind of sit there. You just kind of spin around in a circle, but it doesn't feel like you're being thrown out. And that connects with this physics. You're right here. That the rate of centripetal acceleration is directly proportional to r for a situation like this. So if your r is bigger, you're farther away from the axis of rotation, you experience a greater centripetal acceleration. All right, and the reason is because every point has the same number of revolutions per unit time, and if you're further out, you have to travel a greater distance. So that means you have to be moving faster to cover that distance, that circumference, in the same amount of time. Thus, there's a greater centripetal acceleration. All right. So there is one concept in the homework that we haven't talked about, but see what you do with it. It's the concept of relative velocities. The idea is that, well, here let's connect this with an everyday experience. It's something like this. If you are let's draw a picture. You are on a train. It's an old-fashioned steam engine, of course. All right. You are on the train, sitting down, enjoying some cappuccino, and somebody walks past you on the train. So this person is moving in this direction. And your friend is outside the train looking at what's happening. So the concept of relative velocity is this. To say that something is relative, in physics there's this idea of relativity, and everyone's heard of Einstein's theory of relativity, which is beyond the scope of this course. But there's also a concept of Newtonian relativity, and Newtonian relativity says that certain quantities in physics are relative to the observer, and other quantities are the same regardless of who's doing the observing. And the velocity is one of these concepts, one of these physical quantities that's relative to the observer in classical physics, in Newtonian physics. And so this scenario of the guy on the train is of an illustration of this point, and it goes something like this. If you are on the train, you're this guy watching this guy walk past you. Maybe from your perspective he's moving at 2 meters per second, okay? But if you're outside the train watching this guy move by, it looks like from your perspective that he's moving 22 meters per second. And the reason is because he's moving with the train, and this observer is moving with the train as well. And so that's the essence of relative velocity. If you're a stationary observer not moving with the train, it looks like the green guy is moving faster. If you're on the train, it looks like the green guy is moving slower, because you're measuring that relative to your frame of reference. All right, Tyler, you say, does it decrease in intensity at a constant rate as you approach the center? So yeah, that's a question about the centripetal acceleration. And the formula that we just showed you is that the centripetal acceleration, if your speed is in an angular speed, revolutions per minute, the centripetal acceleration decreases linearly as you get closer to the center of the merry-go-round. So it's proportional to r. It's directly proportional to r. So if you plotted it, it would be a straight line. Okay. So that's it for today. Oh, let me just say one more thing about relative velocities. The trick to dealing with relative velocities is doing vector addition. So if you have, the way you would say that is like the velocity of the train observer, the velocity of the person walking on the train relative to the observer on the train, as compared to the velocity of that person walking relative to the person who's outside stationary. The difference is the velocity of the train itself. So for the outside observer, the velocity of that person walking on the train is equal to its velocity relative to the train plus the velocity of the train relative to the stationary Earth. So you get these additions. All right, but I think you can do that. All right, so that's it for today. So Friday, no live stream. I'll be in class to answer your questions. Sign up and come. I want to see you. All right.